Hi, I'm going to break up sac436 into two parts, problem number one into two parts. We're asked to find the magnetic field at a point P I've indicated on this diagram due to a current that comes in along the negative x prime axis and goes out along the negative y prime axis, or you could call it the x axis and the y axis. And it breaks up rather naturally into two parts. We find the magnetic field due to the wire that lies along the x-axis, and then the magnetic field due to the wire that lies along the y-axis. And the magnetic field at point P is going to be the sum of the contributions from those two wires. So let's work on part one here. The magnetic field due to this wire, which lies along the x or x prime axis. I'm going to characterize the point where we're trying to find the magnetic field in terms of x comma y. We fix a point with arbitrary x comma y in the end. Our answer for the magnetic field is going to depend on what x and y are. So in essence, it's going to be a function of x and y. But throughout the entire problem of finding it, I treat x and y as constants. We're going to be using the Biot-Savart Law, which states that the magnetic field due to a tiny little segment of the wire, dl, depends on how far that tiny little segment of the wire is from the point where you're trying to calculate the magnetic field. I'll call that distance R1. So the 1 for a representative distance from an arbitrary little wire segment along the x-axis. I'll use R2 in part 2 of this entire problem. The Biot-Savart Law states that dB1, I'll call it. No, I'll back up here just a second. Our end game plan is B is equal to B1 plus B2, where B1 is the magnetic field due to this segment of the wire, and B2 is the magnetic field at point P in both cases due to this segment of the wire. I think I want to mention that by the right-hand rule, both of these are going to be in the z direction. If you point your fingers, point the thumb of your right hand in the positive x direction, the direction of this current, the fingers will curl around the wire in such a manner that as far as the plane of the page is concerned, where they come out, they're pointing straight out at you, which would be the positive z direction. And the same goes if you point your thumb of your right hand in the negative y direction. The fingers will curl around, indicating that the magnetic field lines curl around the y-axis. I'd say clockwise, as viewed from a large positive value of y. And that means that as the fingers curl around, they would go into the screen over here and come out of the screen on this side. Point P being on this side indicates that, again, the magnetic field points out of the screen straight at you, that is along the positive z direction for B2. So in both cases we get a magnetic field that's in the positive z direction. The Biot-Savart Law states that dB, I'll call it dB1, again the contribution due to a piece of wire from this particular segment of the wire that lies along the x-axis, is going to be mu0, magnetic permittivity of free space, a universal constant, over 4 pi times I, the current in that wire, times d, I'm going to call it dx prime. That's actually a dl at this stage. crossed into R1, all divided by R1 cubed. Alright, our R1, I'll make that into a position vector. Now, R1 is actually a vector extending from the little wire element to the point in space where we want to calculate the magnetic field. Okay, dl in this case is dx prime. I'm using the x prime and y prime variables to characterize a point on the wire over here. And the x comma y would characterize a point in space. We get two sets of coordinates for the same exact axes. These, as I sum up the contributions to the various points on the wire, the x prime is going to change, whereas the x remains the same. The position in space where I'm trying to calculate the magnetic field remains the same. So let's write that with the dl being replaced with a dx prime. So I got db. I'm also going to take advantage of the fact that we've established that the direction is in the positive z direction. The direction of every contribution to the magnetic field at point P, actually due to both wire segments, is in the plus z direction. So I get the magnitude here. Also, well, the cross product, I do have to worry about the cross product a little bit. So we'll start thinking about that actually in two different ways. Mu 0 over 4 pi times I times dx prime. And I want dl, which is in the positive x prime direction, crossed into R1, which is in this direction. And if you remember what that means, the cross product means, it's you can take it's one vector times the component of the other vector, which is perpendicular to the first vector. Well, the first vector in this case is dl, and it lies in the x prime direction. And R1 can be considered to consist of two parts. A piece, make it a different color for this, a piece along x prime and a piece perpendicular to it. This piece is a length, this component of the vector R1, this vertical component, has length y. The horizontal component, I want to get that in there as well. It's got a length x is this piece, plus this piece, which if I characterize the position of my little wire segment as x prime comma 0, characterizes the point in space where I'm taking a little wire segment that's making the current contribution. And this is the game plan. I find out what its contribution is. I've chosen it arbitrarily, specified its position as x prime comma 0 as opposed to a minus 5 centimeters comma 0. And that means it represents any piece that you want. Each of them having a different actual value for x prime, and then I sum it up for all the possible values of x prime, sum up the contributions to the magnetic field at point P for every possible value of x prime. It's going to be an infinite sum of infinitesimal contributions, and of course it's an integral. Now x prime itself, because this entire wire segment lies to the left of the y-axis, x prime itself is a negative value, something like negative 5 centimeters. So this distance here, if I'm just looking at that as a distance, a positive separation of 2 points in space, is going to be minus x prime. So for instance, if x prime is equal to minus 5 centimeters, then the distance here is minus and minus 5 centimeters, or just 5 centimeters. So the total distance, the total length of this leg, the horizontal component of the position vector of point P relative to the little wire segment under consideration, is x plus the negative x prime, or x minus x prime. This is important because I need to know what R1 is, and it is indeed x minus x prime all squared from Pythagorean theorem plus y squared, with the square root being taken of that entire expression. So in magnitude, that's what R1 is. I'm going to go ahead and make it clear that I'm indicating the length of this vector R1. Okay, now getting back to this part, we were doing the cross product. dl crossed into R1 means, in magnitude, the magnitude of the vector dl times the magnitude of the component of the vector r1 that is perpendicular to dl. Well, the component that's perpendicular to dl is this segment labeled y, segment having length y, and so in magnitude this cross product is just dx prime times y. And I'll put that all over r1 cubed. And we recognize that the whole thing is in the direction of the positive z-axis. I want to briefly, we don't want to leave it on the page, but look at a different way of doing that gives you the same result. If we work this out in IJK notation, in particular this cross product. So let's take a look at that cross product. We'll see that we'll get a vector that's in the z direction, and indeed it'll have this same magnitude. So I just want to look at dl cross r, which we have argued in a conceptual manner turns out to be dx prime times y in magnitude, and it's in the z direction. This can be written as dx prime times the unit vector in the I direction. So unit vector in the I direction is in the positive x prime direction. The unit vector in the y direction would be in the positive y prime or positive y direction. And a unit vector k in the z direction is coming right out of the board at you. So here's the dx, and it's pointing in the I direction, so I can write it as a total vector in IJK notation as dx prime times I. And then the r can be written as, well, it's a step. Here's r, it extends from here to here. It's a step along the x direction of x minus x prime. I'm going to make that into some square brackets there. X minus x prime times I, and then plus y, a step along the y axis, times j, and that's the vector r1. So I do that cross product. This part crossed into this part gives me 0, because I wind up, as far as the vector direction part is concerned, is I crossed into I, and vector crossed into itself is of course 0. And then I crossed into j by the right hand rule. First it's going to have unit magnitude, but point your fingers in the x direction, arrange the hands so that if you start closing the fingers they point in the y direction. So fingers in the direction of the first vector I, arrange the hands so that if you close them, they point in the direction of the second vector, which is J in this case. And you see the thumb points out of the screen, which is in the K direction, in the positive Z direction. You get, I say magnitude, of course, 1, because the two vectors in the cross product are perpendicular to each other, and each one of them has the length of 1. So I wind up with dx prime times y. So I'm taking this term, banging it into that one. You've got the magnitudes out front, and then the I crossed into J is just K. So plug that into this original expression for dB1, and I've got just what I got down below, except on the right hand side I've got times the unit vector K, and on the left hand side I've got the vector dB1. But I'm just dealing with a magnitude here, and that's exactly what we said. That would be a vector dB1 in the plus Z direction. This whole thing multiplying K hat, and hence we get the same result, whether we argue this at a conceptual level or we look at it in terms of IJK notation. So I want to get rid of that and start working on this actual vector here. On this, what's going to turn out to be an integral. So this dB1 is a contribution at to the magnetic field at point P due to this infinitesimal little wire segment at x prime comma 0. Now if I add up all such contributions from all such little wire segments along this negative x-axis, I'm going to get the total contribution to the magnetic field at point P due to this entire wire, which I'm calling wire 1, the one that we're working on this part of the problem, part 1 of the problem. So I've got to integrate. Just say the sum on this side, infinite sum of all the little contributions, dB1. And on this side, I want x prime to run from minus infinity all the way up to infinity. So over here on the left, sum up all the little contributions, you're just going to get the total. B1 in magnitude, and we know it's in the positive Z direction, is mu 0 over 4 pi times I times the integral, and I think I said that goes up to plus infinity. Actually, this wire ends at 0. So we're going from minus infinity to 0 on this integral. And y is a constant throughout this entire integration. So I'll go ahead and factor out the y. Now we're talking about the magnetic field at point P. Got all these contributions to it, but point P is fixed in space, so the y value isn't changing. So I've got the integral from minus infinity to 0 of dx prime divided by the R1 cubed. I've got an expression for R1 up here. I could write that instead of square root, raise it to the 1/2. In fact, let's do that. That's x minus x prime all squared plus y squared. Okay. Y squared all to the 1/2, and if I cube that, that would be multiplying this exponent by 3, so I have the same thing raised to the 3/2. Go ahead and copy that down here. X minus x prime all squared plus y squared all raised to the 3/2. So now I have to evaluate that integral. And if you look on the formula sheet or in the back of your book where you've got a table of integrals, you'll see that this one is pretty similar in the form to, I call it a generic expression, dx over x squared plus or minus a squared that you find in the table of integrals, all to the 3/2, and that's equal to, that evaluates to plus or minus x over a squared times the square root of x squared plus or minus a squared. So you look at it, we've got a similar thing. This is saying we're integrating over x. We get the variable x in the denominator and a constant squared, and it's all raised to the 3/2. And we get something very similar. The y is the constant playing the role of a, but instead of just an x, the variable of integration, which would be actually an x prime in our case, we've got this expression x minus x prime, so it's not quite identical. Of course, we're dealing with the plus sign, so we don't even need that minus part. I think I'll just erase that. So for us, we're just dealing with the plus, and don't need it if not distinguishing it from the other case. And it appears one more place. So this is the integral. If we can get ours in this form, then we can just use it directly. To get ours in that form, I'll do a variable substitution. I'm going to call the variable u just x minus x prime, and if I can make that the variable of integration, if nothing else changes too much here, I'll have it exactly in this form, variable of integration squared in this position, as opposed to some difference in two things squared. If this is the case, continue the variable substitution. Du would just be minus dx prime, because again, for purposes of integration, x is fixed up here in the picture. We're keeping point P fixed and adding all the contributions from the various points along this wire to the magnetic field at point P. So point P being fixed means x is a constant for purposes of integration here. And then make that substitution directly in there at that stage. Well, let's figure out what the limits of integration would be if our integration variable is u. The upper limit, u when x prime is equal to 0, is going to be equal to just x. And u when x prime is equal to the lower limit, the minus infinity. If I plug in a minus infinity here for x prime, I'll get x plus infinity, which is infinity. And I think that'll do it. The dx prime that I have in the original integral becomes du, obtained by multiplying both sides of this equation by, it becomes minus du by minus 1. And I just have room to write this b1 as an integral of this variable u. It'd be mu 0 y I all over 4 pi times the integral from infinity up to x, or I should say down to x, of minus du, I think I'll put the minus sign all the way out front here, divided by u squared, and that was why I made the substitution to keep that simple. Plus the y squared, it's just a constant, it stays the same. All to the 3/2. And the integral piece looks a lot simpler that way. I think I'll take the minus sign and use it to switch the limits of integration. I think you recognize the integral from a to b is equal to the negative of the integral from b to a, and so I'll take advantage of that fact to write this without the minus sign. I find it slightly easier to evaluate if I don't have minus signs floating around. That's du all divided by u squared plus y squared all raised to the 3/2. And now, I can get it in the same picture. This does look, it has the same form as the integral up here. So this just becomes, I'm going to squeeze it in here just so I can see it. So mu 0 yi all over 4 pi. So I can be looking at both pieces at the same time. I need the x, which was the variable of integration, so that would be the u here, divided by the constant squared. The constant squared is a here, but it's y in our problem. And then times the square root of the variable of integration squared plus the constant squared. And this all has to be evaluated, in our case, from the lower limit of integration, the x, up to the upper limit of integration, infinity. Okay, so we just squeezed that in there. I think I'll go ahead and evaluate it. That's mu 0 yi over 4 pi times this u at infinity. So evaluate the expression at the upper limit. And actually, I'm gonna factor this y squared out, so I don't keep copying everything down. I'll go ahead and take advantage of the fact that a y up there cancels out one of those. But now, I'm just evaluating this piece. All that part's a constant, so I'll just multiply it. And then I'm evaluating this piece from x to infinity. And I got part of that written already. Infinity up top divided by infinity squared plus y squared, and then minus the same expression evaluated at x. So x squared plus y squared. This business, evaluating it at infinity, the mathematicians will tell you you're really taking the limit as u goes to infinity in this expression, but you should note at that limit goes to 1. Down here we got something that essentially amounts to the square root of infinity squared, which is infinity. Divide that into infinity and you get just 1. So I write that as 1 minus x over the square root of x squared plus y squared. And that's the magnitude of B1. It's in the z direction. I can call it a vector in the z direction just by putting a hat over it and multiplying it by a unit vector in the z direction. That's actually our final answer for part 1. And the next screen cam will be one that involves part 2, I'll give you a glance ahead, say in part 2. We will find that B2 is equal to mu0I over 4 pi x times 1 minus y over the square root of y squared plus x squared. Actually, could write it the same way as what we have up there. All times k hat. And if we put those two together, the total B. So B2 is, of course, the magnetic field at point P, the contribution to the magnetic field at point P due to this vertical wire segment in which the current travels in the minus y direction. The total B will just be B1 plus B2, and once we add them together, we're going to find out that the total can be expressed as mu0I all over 4 pi times 1 over x plus 1 over y minus the square root of x squared plus y squared, all divided by xy. And again, this whole vector is in the z direction, so all multiplied by the k hat. So this will be our final answer after we finish up part 2. This up here, this expression for B1 is actually our answer for this